Hi class. In the first part of Chapter 6, we talked about basic lenses and how the eye works and cameras and basic things about how light bends through lenses. And we talked about reflection and refraction. So now we want to look at general ideas of some of the general ideas of telescopes, the different basic designs there are of telescopes, what some of the important factors are, what we call powers of a telescope, what are the important powers of a telescope, and then just some basics about what astronomers actually do with telescopes. So there's actually three powers of a telescope that you might talk about. One is light gathering power, or light gathering area. The other is angular resolution, and the other is magnification. And actually magnification is not, I mean, it's important, but it's not that important. It's the least important one. So if you were to go buy a telescope, you would never want to buy it based on an advertisement that said that it's a 200 times telescope, for example. It's really meaningless, and we'll talk about why. So what is this light gathering power and this angular resolution power? Well, a telescope has a certain area. The mirror or the lens that the light goes through has it's a certain size, and so it can gather a certain amount of light. If you think about a storm, if you're out in a storm and you want to gather water to drink, would you put out a little cup, or would you put out a big bucket? You definitely put out a big bucket because more water would be collected in that big bucket. So in the same way, we're trying to collect light. So instead of putting out a little bucket to collect light, a small telescope, in diameter we're talking, you would put out a bigger telescope. Bigger telescope's going to collect more light. Objects are going to look brighter. It will take you less time to gather a certain amount of energy to be able to see the object if you have a bigger telescope than if you have a smaller telescope. Angular resolution is also an important thing, and we'll look at some pictures to see kind of what that means. But both of these things depend on the size of the telescope, the diameter of it. The bigger the diameter, the better both of these powers of the telescope are. So the light collecting area, light gathering power depends on the area of the mirror or lens, and most often these mirrors and lenses are circles. So the area of a circle is pi times the radius squared. The radius is the diameter over 2. So really it's related to the square of the diameter. If you were to double your diameter, make it twice as big, so go from like a 1 meter diameter telescope to a 2 meter diameter telescope, that actually increases the area by a factor of 4 because of the squared here. So increasing the diameter significantly increases the area, and the light gathering ability of a telescope is directly related to the area of a telescope. The biggest telescopes nowadays are around 10 meters in diameter in that area. And we'll talk later about how we can use multiple telescopes to actually combine their images, to combine their information, to make it sort of act as if it's a much, much larger telescope on the order of kilometers in diameter. And then if you do that, you get really good. Doing that doesn't help a lot with your light gathering ability, as we'll talk about, but it really helps with the other power, the angular resolving power, angular resolution. How does the collecting area of a 10 meter telescope compare with that of a 2 meter telescope? So going from a 2 meter diameter telescope to a 10 meter diameter telescope, what is the factor difference in those two? 10 is 5 times 2, so we're going from a 2 meter to a 10 meter, we're multiplying the diameter by 5, but remember that 5 is going to be squared when we talk about the area, so 5 squared is 25. So it's going to be 25 times greater in area, and so it's going to have a 25 times greater ability to gather light. It's going to gather 25 times more light energy than the smaller telescope. So astronomers try to make the biggest telescopes they can. So angular resolution is another thing that depends on the size of the telescope. And what this has to do with is whether you can see two objects as distinctly two objects rather than a single object. And this image shows two people looking at a car, and this person sees a car far away, this person sees the car much closer. Let's say it's the same car. There's a certain distance between these two headlights. Those are two definitely distinct headlights. But the farther away they are, the harder it might be to see that they are actually two headlights. This angle here is the angular separation between the two headlights. As the car gets closer, that angular separation gets larger. And so if the car is really far away, the angle is going to be really small. And if your telescope has good angular resolution, it will be able to distinguish between those two headlights. It will be able to see them as two separate dots of light. If the telescope is small and has a small diameter, because of the properties of light and going into the telescope, we'll look at in a second, the angular resolution is not as good, and the telescope won't be able to distinguish one headlight from the other. You'll see it'll look like one blob of light. You won't be able to tell the difference. We can look at one of these interactive figures that we've played with before. Maybe not this one in particular, but we've played with many interactive figures so far in these lectures. And here's one from our book, and it shows this dot of light down the road here. It looks like it could be a motorcycle, could be a car, we don't know, it's so far away. And so when I click start, it'll start coming toward us, and you'll see at some point we'll be able to tell whether it is a single light or whether it's actually two lights. So here it comes, and there we can start to see two lights, and now definitely it's two lights. And so our eyes, when the car was far away, our eyes didn't have a good enough angular resolution to be able to see that there's actually two lights there. The angular resolving power of our eyes, if this was in fact what our eyes would see, our angular resolving power is not very good. It's not as good as, something bigger like a pair of binoculars, for example. And so it's not until the car gets a little closer so that that angle gets bigger between the two headlights that we can actually see that there are two headlights. So that's the idea of resolving power, resolving detail in an image, or being able to say that there's two objects at a great distance rather than just a single object. These two stars right here in the night sky behind the car, we can clearly see there's two little dots of light there. But when we look at one of these other stars, we can't really tell. It looks like a single star, but it's possible that there's actually two stars really close together there. We just can't tell. Our resolving power just isn't good enough. So telescopes with big diameter have two big important factors. They have better light gathering power, and they have better resolving power. The reason why resolving power depends on size has to do with how the fact that light behaves like a wave. And when light goes through a small opening, even a large opening, any kind of an opening, the light kind of bends as it goes through the opening. And when the light hits the sensor that you're forming an image on, like the camera film or the CCD chip in the camera, when light hits the sensor, because light came through a circular opening, it leaves these circular, almost like ripples, fuzziness on the image. A little pinpoint source of light that you take a picture of is not going to leave a little pinpoint dot of light on your sensor because of this thing called diffraction, the bending of light as it passes through openings. The image you're going to get is actually going to be like a dot with like circles around it almost. And so if this is a dot that you're getting of light on your sensor, let's say from a star, and this is another dot from another star nearby it, if there is none of this diffraction stuff going on, then you're going to see two dots on your film. And you would ultimately be able to tell that there are two stars. But there is this thing, this diffraction thing. There's nothing we can do about it other than to make our telescopes bigger. And so the images are always going to have these little circles around them. Sometimes they're hard to see because, these effects are fairly small. But if the stars are really close together, these circles for each star are going to overlap with each other. And when you look at the image, you might not be able to tell that this is two different stars. The whole fuzzy pattern you might see here might look like a single star. You might not be able to tell that it's actually two stars because of this fuzziness, because of this diffraction. It has nothing to do with focusing. It has nothing to do with whether your camera or telescope's in focus or not. It has simply to do with the fact that light behaves like a wave as it's traveling, and as it travels through openings, it spreads out, and that's called diffraction. And so as it travels through your telescope, through the opening of your telescope, there's some spreading going on, some diffraction going on, and that causes every image to have some fuzziness to it that we just cannot get rid of. We can minimize it, we can try to diminish it. There's a lot of techniques for doing that, but you can never get rid of it 100%. So here's a picture of just what I was talking about, a star, and you can see the rings. We've zoomed into this image from the Hubble Space Telescope. The Hubble Space Telescope has a certain diameter, And so every single image it takes of a star is going to have these, it will have these rings around it. And this is a highly zoomed in image of a star, and the actual picture that the telescope took probably had a bunch of stars in it, but we zoomed in to one particular one. And if you zoom in far enough, you can see these rings around the image of the star. These are those diffraction rings that you see. So if there are two stars that are close enough together where their rings significantly overlap, you won't be able to tell that they are actually two stars. You might just see one blob of light in there. So there's a certain limit. There's a certain angular diameter. If two stars are closer than that, if their angular separation is closer than that, then these fuzzy rings are going to overlap and you're not going to see them as two distinct stars. That smallest angle that you can resolve is called the diffraction limit. And it's simply because of the fact that your telescope has a certain size. There's nothing you can do about it. You can do some processing of your images to try to minimize it. And as I said, you could combine your image with images from other telescopes of that same object taken at the same time. And we'll talk about how you do that, but combining those images from other telescopes can actually help you reduce the diffraction, but you'll never get rid of it completely. So the images will always have some sort of fuzziness to them. But the bigger the telescope, the less of a problem it is. So what are the two different designs that you might see in telescopes? There's two types. There's refracting telescopes and there's reflecting telescopes. Telescopes that have lenses that focus the light with lenses are called refracting. Telescopes that focus light with mirrors are called reflecting, as you might expect. So here is the world's largest refracting telescope. It's got a lens way up at the top, and it's a very long telescope because the light bends through the lens, it comes down, focuses way down here, actually focuses inside, but then it diverges a little bit more. It goes into an eyepiece and then focuses ultimately onto a film or something. The combination of the eyepiece and the lens here gives you the magnification. But this is called the primary lens up here. That's what does the initial focusing of the light. And that's a big lens. That lens is over 1 meter in diameter. It's very heavy. It's a big chunk of glass. And it has to be supported only on the edges of it. So when you create a refracting telescope, you have to take a big piece of glass and you have to make the shape just perfect. And you have to support it only on the edges. It's very heavy. This is really hard to do. So this is the world's biggest refracting telescope, and it actually is up in Williams Bay, Wisconsin, on the west side of Lake Geneva, Lake Geneva, and it's within an hour of our campus. And so if you ever have an opportunity to go up there, they have tours on the weekends, in the mornings, and also I think on most weekdays in the mornings as well. They have a website you can go to. They do ask for donations. It is a working observatory. They don't use this telescope that much for research anymore. There are other telescopes that they use, but they give tours of this. You can't actually go and use the telescope, but you can go in the dome and walk around on the perimeter here. The whole entire floor rises up and down as the telescope points in different directions. The back end of it goes up and down, and so you have to go up and down with it if you're going to be observing through it or using, adjusting things with cameras on the back. This whole entire floor rises up and down. So it's a pretty impressive observatory. So if you ever have a chance, this is the Yerkes Observatory. If you ever have a chance, I'd highly recommend going. So refracting telescopes are hard to make. And that one, the Yerkes Observatory one, was made in the 1800s, late 1800s, and it's the world's largest still because they're just hard to make. And it's just much easier to make a much larger reflecting telescope. So here's an example of a big reflecting telescope, a really big shiny mirror here. And these telescopes, the biggest ones are around the 10-meter diameter range, and they're getting bigger as technology improves. So the light comes in, it bounces off this big mirror, hits a secondary mirror up in here, and then bounces back into the hole in the center. There's a hole in the mirror, and the light goes back down there, and then goes into your instruments, cameras, or whatever you're using. So there's a few different designs of reflecting telescopes. In all the designs, though, they all have a primary mirror that the light hits first. And then in this design, it bounces back toward the center, hits a secondary mirror, and ultimately focuses at a point behind the primary mirror. Here's another design where the light comes in, hits the primary mirror, bounces forward, hits a secondary mirror that's at an angle, focuses off to the side. And then here's another design that's very similar. Light comes in, bounces forward, the secondary mirror is here, bounces again, hits this one, and comes off over here. So there's advantages to these different designs. You don't have to memorize the names of them, but just know that there are a variety of designs. And you might be wondering, well, you've got this secondary mirror that's actually inside the telescope, and yeah, it blocks some of the light coming down from the stars, so you do get some blockage. The mirrors are really just donuts. They're big donuts that have a certain diameter. There's usually a hole or at least a spot in the mirror where light never actually hits it because of the shadow of the secondary mirror. But that's okay. As long as we have enough mirror available to collect light, we'll get a brighter image than we would with a much smaller telescope. And so these mirrors, one of the advantages of these reflecting telescopes, is that these can be supported from behind. They might still be heavy pieces of glass, but that's not as big of a deal anymore because you can support them from behind. You don't have to, light doesn't come through them, light just bounces off of them. And so the shape you have to make it's only critical to make the right shape on one side of it. The back of it can be flat or it can be any shape you want, really. But only one side has to be curved just right to get the light to bend properly. A lens has to be curved perfectly on both sides. The light has to pass through it just perfectly. And then again, it has to be supported on the edges. So the refracting telescopes are much more difficult to make. The big heavy glass lenses are harder to grind, harder to make, have just the right shape. So here are some examples of reflecting telescopes. These two telescopes kind of work in tandem. This is in Hawaii on Mauna Kea, and this is the Keck telescopes. There's two of them, and they're each 10 meters in diameter. They have a segmented mirror. If you look closely here, the whole mirror is this big thing, and it's made of a bunch of segments. If you can kind of see the lines drawn in here, they're little six-sided segments that the mirror is made of, and they're all kind of stitched together in a way. And you might think, well, there's all these cracks in it. Doesn't that blur your image or do something? Well, no. It's just that they all act like little mirrors, and they send light in the same direction. So every one of these little mirrors acts like a little telescope, in a sense. Not so little, really. But they all kind of work together, and they shine light back toward the secondary mirror, and they all kind of work together to form an image that a much larger telescope would form. You can see a person sitting in here to get a kind of an idea of how big this thing is. This person's kind of squatting down. There's like a cage on the front end of the telescope where that secondary mirror is located, and you can sit in there if you're given permission to. So that's the big 10-meter telescope on Mauna Kea, and we'll talk about how these two telescopes work together. They can actually kind of look at the same object at the same time, and when you combine the images of these two objects, the resolving power that you get is the same as you would get if you had a telescope that has a diameter equal to the distance between these two telescopes, which is several meters, maybe 100 meters. So it's the same resolving power as a much, much larger telescope, and that's really important. Resolving power in astronomy is probably one of the most important things. Light gathering power is important too, but you can always increase the amount of light that you're collecting by increasing the amount of time that you're developing your exposure, or you're not developing, but you're collecting light for. Resolving power, the only thing you can do to improve that is by making a bigger telescope. And so you can kind of fake that there's a bigger telescope by using two telescopes in tandem that are a large distance apart. That's called interferometry. So what do astronomers do with the telescopes once they have them? What do they do? Well, there's a variety of things they do. Imaging, spectroscopy, and monitoring, timing of things. So imaging is just basically taking pictures. And what they often do, though, is they take a picture of an object several times through different filters. So they'll take a picture of an object through a blue filter, so that only the blue light goes through. And actually, astronomical cameras are really black and white cameras. You don't use a color camera in astronomy, except for amateurs like me that might be taking pictures through my telescope in the backyard. I would use a color camera, but I might not. If I had a dedicated astronomy camera, it would be a black and white camera, and I would put filters in front of it to take one picture through the blue filter, one picture through the green filter, and one picture through the red filter, and maybe other filters as well. And then you use software to combine those three images to get your final image of the object. Doing it this way allows every single pixel, every single sensor in your camera to detect every single color. In a color camera, there are different sensors for different colors, and you have to put them all onto this one sensor, and so that wastes a lot of space. If you have an image that is just giving you red light, then you're only going to be using the sensors in your camera that detect red light. And so some of those sensors are just not going to be used. They're going to be wasted. So you can get much better resolution in your image if you allow every single sensor to see the light that you're using. And so you use a black and white camera where every single sensor can capture the light, but you put filters in front of it so that you only allow through those different colors. And you just have to keep track. Okay, this picture number 1 I took is actually through a red filter. You have to keep track. It doesn't look red until you actually make it red in the software. And so you have to assign a certain color to it based on that filter that you used. So that's what astronomers do. They take pictures through different filters and they combine the filters together to form your final image. We have another little interactive figure that kind of shows how that works here. Here's that picture, and we're showing the actual picture of the object, and I can turn off the different filters. So if I turn off the red filter, the part of the image that's red, and I can also turn off the green, this is what you would get by just looking at the blue, the image through the blue filter. Everything looks blue. If I turn that off, of course there's nothing, but now I just turn the green on, and that's where all the green light is coming from, all those objects. So we're looking at light coming through a filter. So anything that's giving off red light, we're not seeing right now. But there's a lot of this stuff that's giving off all the different colors too. So we are seeing things that are giving off red light. We're just not seeing the red light that it gives off. So if I hide the green and show the red, it looks fairly similar, but there is a slight difference. Let me turn the green on again. You can kind of see I'll turn the green on and off, and you can kind of see some details that appear and disappear as I turn the green on and off. So there are some areas that kind of come into better focus in a sense, resolved a little bit better when I turn the green on, and then when I turn the blue back on, then you get the full picture of it. So the red, the green, and the blue are your typical filters, but there are others that astronomers use. So here's an example of imaging through X-rays. So we'll talk about different types of telescopes in the next section. In the next 2 sections, we'll talk about telescopes that detect X-rays. So X-rays are a form of light, and they don't have a color per se, but they have different wavelengths. And we know that shorter wavelengths means higher energy. And so you design a telescope that can collect X-rays, and you design some kind of a camera that can sort of capture those X-rays and measure their energy. That would be like measuring the color. That would be like your color filters. And so you design some sort of a detector that can measure the energy of these X-rays that come in. And then what you do is you make a map. You kind of draw out on your sensor where the X-rays are hitting, and you color them according to their energy. And so you might color them red if they're low energy X-rays. So any of the red blobs are places where there's X-rays coming from, but they're fairly low energy X-rays. The green areas are where there's sort of medium energy X-rays, and the blue areas are where there's much higher energy X-rays. And so this is called a false color image, because the light itself that's coming to you, X-rays, it doesn't have these colors, but we're just coloring it to give our eyes a way of understanding, what's more energetic. Where are the more energetic X-rays? Where are the less energetic X-rays? And that gives us an idea of what this object looks like in terms of where X-rays are coming from. We can also do spectroscopy, and this is what we did a little bit of in Chapter 5. In class you might have used the diffraction gratings, and I demonstrated that a little bit in one of the videos in Chapter 5. But the diffraction grating was something that you can look through, and you saw the different light sources, and you saw the different colors that those light sources emitted. For a light bulb, you saw a continuous spectrum of red, white, or red through purple. For hydrogen or helium gases, you saw certain particular wavelengths that they emit. And so that was what's called a transmission diffraction grating. The light was transmitted through it, and when the light went through it, it split up into its different colors. You can do the same thing with telescopes. What they use, though, is a reflection grating. So this is this thing kind of like what you look through, but the light reflects off of it instead of going through it. And once the light reflects off of it, it breaks the light up into its different components, and those things get focused onto a film some kind of a device that captures the spectrum. And so here's a telescope up here, here's the primary mirror. The light ultimately comes in, bounces off the primary mirror, goes up to the secondary mirror, comes back down, comes to a focus. It goes through a slit or maybe into a fiber optic cable or something, and that allows you to select the star or the planet or the galaxy that you want to measure. And then only the light from that star or galaxy or whatever it is comes into this part of the in the back here, the spectrometer. It goes along, the light you can kind of see is diverging as it comes. It comes up to this mirror here. This is called a collimating mirror. What that does is it takes these diverging rays and it makes them all parallel to each other. So there's a lot of stuff here, but you can see these rays of light are kind of coming in now parallel to each other, so that all that light hits this diffraction grating. And then once it hits the diffraction grating, then it kind of splits up that light into its different colors, and then that light comes back toward this mirror, which focuses that spectrum onto a sensor, onto a camera or something like that, so you can actually take a picture of the spectrum that you see. So we use this then to identify chemical elements that things are made of, molecules, and ultimately the temperature of objects, looking at what colors are emitted and how bright they are. And so we'll talk more about this in later chapters. We did talk a little bit about it in Chapter 5. Another thing we can look at when we do look at spectra though, what we're seeing often are absorption spectra, and so the light has a certain brightness. So what this top graph looks like, it looks like brightness and wavelength. And so the brightness has some value for these wavelengths, and then as you get to these wavelengths, the brightness goes down. That means some light has been absorbed for these wavelengths, and then the brightness goes back up. So there's some chemical, some molecule that's absorbing light that's coming from whatever this object is that you're looking at. Well, there's not a lot of detail here. It's kind of hard to see what's going on. And so if you had a better diffraction grating, so this diffraction grating is something that you can construct and make it really good. And if you have a really good diffraction grating, you can actually get better detail in this spectrum. And so the spectrum might look like this instead. You can see there's a lot of absorption at this particular wavelength here. There's a lot of absorption at this wavelength. There's a lot at this wavelength and a little at this wavelength. And so then you can really more clearly identify where these major absorptions are happening. And that will then more clearly kind of tell you what the elements are, what the molecules are that are absorbing this light. And that tells you then what that object maybe is made of, or at least what's maybe in the atmosphere of that object. And then the last thing we can do, well, not the last thing, but one of the last things we can do is our timing experiments. So we can look at objects and see how their brightness changes over time. And this is useful for things like planets, looking at planets that are going around stars. If a planet happens to go around a star, and from our line of sight, from our perspective, the planet goes directly in front of the star every time it goes around, then we should see a dimming in the starlight. The brightness of the star should go down. And then as the planet leaves and goes back around, the brightness should go back up. And then when the planet comes back in front, the brightness goes down, and so on. And so we may see with a planet going around a star, we call this an eclipsing exoplanet. It eclipses the star, or we would call it a transiting exoplanet because it transits across the star, sort of across the surface of the star from our perspective. We would see this increasing and decreasing brightness of the star. That's one example of where you would use this. Other examples are there are some stars that just simply change brightness just because that's how they work. They're called variable stars, and it isn't necessarily because something is going in front of them, but rather it's just because of how they're operating, how they're producing their energy. They produce it in these cycles that kind of grow and shrink and grow and shrink and so on. And so you can measure the brightness of stars as it changes over time and learn some properties about those stars. So the last thing is, if you want to buy your own telescope, I mentioned this a little bit, don't think about magnification. Forget about it. The only thing you really want to worry about is the size of the telescope and the quality. And you also want to make sure the mount is stable. It's going to be mounted on something. Make sure the mount is a stable mount, a stable tripod. And don't get something too big and heavy that you can't move it around, because you just won't use it anymore. So you might even consider, before you buy a telescope, to first buy a good pair of binoculars. You can see an incredible amount of stuff just by laying on a little a pad or something, or lawn chair in your backyard, taking some binoculars and just looking up. and just look around. It's really incredible what you can see. But if you want to buy a telescope, find a good quality telescope. There's some good brands out there. Astronomy Magazine, Sky and Telescope, and other websites advertise, and they give reviews on certain equipment and certain telescopes. Look at those reviews. Meade, Celestron, Orion are three quality manufacturers of telescopes. They're all good. They have slightly different ways of working, but they all will give you good images, and they'll be useful for a long time. So this chapter, or this section at least, was about the main ideas of telescopes, the main properties of telescopes, and so light gathering power and resolving power are the big things to think about. And then the two main types, refracting and reflecting. And we mainly use reflecting telescopes now because they're easier to make, and we can make them much, much bigger, which is really important. And then we do these different things with telescopes: imaging, spectroscopy, and time measuring or monitoring. And we'll come back to all these different things as we learn about objects in the sky, like galaxies and stars and things like that. So that's all for now. Have a good afternoon.